Hello there, thanks for watching and I appreciate you. This is a video in a series of videos showing you how to make a custom character controller that uses rigid body physics, cinemachine cameras, Unity's new input system, and custom player gravity. In the last video we added the ability for our character to run. Wasn't a very exciting video to be honest. In this video though, we're going to handle slopes, and this is a very exciting topic in my opinion because everywhere I've seen it done, they just kind of basically slam more gravity down on top of the character instead of fixing the actual problem. I think it's a terrible way of handling the problem, and so in this video I'm going to break it down and we're going to try to handle it as properly as we can. This video is going to include going up and down slopes smoothly, going up slopes slowly and down slopes more quickly, because it makes sense, it's harder to go up a slope than down a slope, right? And also setting a maximum slope angle that we can actually go up, aka or climb. So if all that interests you, you're watching the right video, let's get into it. Okay, so before we can fix the problem, we first need to understand what the problem is. So I'm going to take a minute to talk about what's going on here and what the problem is and how we're going to fix it. So on our screen we have our character controller, right? We have our capsule collider right here, and we're looking at him from the side. So for example, this would be his eye, and this would be his smile, okay? And he's going down a slope in this direction. So what are we doing? We're getting input from our gamepad and our keyboard, our movement info, right? The mouse is just for looking around. It doesn't move the player, but our keyboard moves the player. And how many inputs do we have? We have 4 keys on a keyboard, same as a D-pad. D-pad also just has 4 directions. A thumbstick on a gamepad's a little bit different, obviously, but for the most part, it has 4 directions. It has a forwards and backs, a left and a right, a 2D vector. And we're taking a 2D vector and applying it to the motion of a 3D character in a 3D environment. And obviously the gamepad and the keyboard, they ain't gonna know that. They're just gonna supply this input info, and we're moving our character based off that 2D info. So what would make sense to do then, if that's a problem and we need the movement info to take into account the terrain, then what it would make sense to do is to alter, you take that basic info and you alter it based upon the terrain, and then you apply it to the character, right? So that's what we're going to be doing. To give you a visual idea of what is happening here when you go down a slope and why it skips, I drew this here. So if we're applying a 2D movement vector to our player, then all we're doing is we're pushing him this way to go forward, this way to go back, and left and right, right? It's just square on. It doesn't care about elevation or angle or any of that. And what happens when you apply a force to the back of the character to push him forwards? He just wants to go forwards. He doesn't want to go down the slope. He wants to go forward. And what ends up happening is you get a bounce. And again, the reason you get the bounce is because you're trying to go out in the air, and gravity's like, hey, no guy, you gotta go down. So then they're fighting each other. Because technically, this force is pushing out in the air. It's technically kind of pushing you upwards, and you have a downward force that's constantly being applied. Even if you don't have a downward force constantly being applied, if you go out here, your ground check is then going to clear, right? Because you're going to have a distance, and then it's going to engage, and that's going to make your bounce even bigger. So generally what people do is they just apply a constant amount of down force that keeps their player grounded the whole time. That's not ideal. It's not a good way of doing it. Some games it's probably fine. A lot of games it's probably fine. In this character controller and the type of game that I'm putting together, this is not okay. So again, what we're going to do is we're going to take our input and we're going to alter it based upon our terrain. So that basically, instead of pushing our character here, right, pushing him that way, we're going to push him that way. And that's going to give us a nice smooth descent. And vice versa, if he goes backwards or if he's facing up, we're going to just push him up at an angle, and then that's going to push us up nice and smoothly. Now that's just to handle going up and down slopes and the smoothness factor. The rest of it we'll cross that bridge as we get there. So for now we're just going to tackle this problem first. And now that we've talked about that, let's go ahead and let's jump on over to Unity. And here is our character controller project in Unity. If you've been following along with the series so far, then this is the base that we're going to be working with, of course, because we are continuing the series. If something you see here doesn't make sense, it's probably because you haven't watched any of the other videos. I suggest you go back from the start and you watch them all. We're not that far into the series right now. It won't take you very long to do, and there's a lot of information in there that'll probably help you. Okay, and all we're going to do in here now is we're going to edit our humanoid land controller script. So down in the project panel underneath scripts, controllers, we're going to double click on our humanoid land controller, launch it in our editor. Let's start making changes in our script. So in all of our variables at the very top under the gravity section, I'm going to go ahead and I'm going to change _gravity to _gravity grounded. And just below that, I'm going to add another line as well. And this is a variable that's going to store our max slope angle, which is basically going to be the maximum angle our player will be able to climb up. I'm just going to set it to 47.5 degrees for now. And of course, you can set this to whatever you like. Going back to the gravity grounded, I am changing this a little bit. We're going to keep our gravity local to our fall gravity function. And instead, I'm going to make sure I implement a means of introducing a constant amount of gravity even while we're grounded, because I do see that being useful and a lot of people are going to want that, and I may even need that. So we're going to make sure we implement it. And I'm actually going to change the default value from 0 to -1 so I can make sure it's working properly for now. And at this point, there's quite a bit to do, so I'm going to go ahead and type this all in, and then we'll come back and we'll review the first bit of it. And time to review what we just typed. We'll go to our main fixed update game loop here. All we did here was we took our player move and we moved it to the top just underneath player ground check. We added a player slope function. We moved player run above player gravity, and we renamed player gravity to player fall gravity. And then we removed from our player move function our rigid body mass multiplication. We were multiplying our rigid body mass times our player movement input. And we are no longer doing that there. We're just doing it as a single line in our fixed update game loop. And I added a little note that this is just for development purposes. It's not something you'd usually want to leave in a game. I just leave this so I can change my mass to 1 or 60 and just have some fun with the physics. Okay, let's move further down. Player move, we removed everything, and all we're doing is we're just returning a vector 3. We're using this. Oh, I missed a line here. We don't need this here. We're multiplying our x by our movement multiplier and our z by our movement multiplier. We are not multiplying our y by anything because we don't need to. We can just pass that through. We'll come back to the player slope function. This is where the magic happens. Wink, wink. Under the player run function, I added a input.moveIsPressCheck in addition to the input.runIsPressCheck. And we are now, instead of just multiplying the run multiplier by the x and z, we are now multiplying everything because we're now also using our y to move up and down, since we are constantly changing. Well, we're about to get into that, but we are using our y for movement now as well. So we need to make sure that we're multiplying everything by the run multiplier. And then in the player fall gravity, again, we renamed player gravity to player fall gravity just so it's a little more descriptive and obvious what it does, because it's not going to be handling all of our gravity anymore, just our fall gravity. So this is basically just a timer that increases gravity over time. Again, we changed gravity. It's no longer a global variable. We're just making a local variable. So there's no longer an underscore gravity, it's just gravity. So we created the variable here. We gave it the player move input.y value. We removed setting it to 0 from the if player is grounded check. If the player is grounded now, all we're going to do is we're going to reset our fall current to our fall minimum. Otherwise, if we're not grounded, we're going to do our count and we're just going to accrue gravity as we normally would. We did make one little change here. I moved this line out of this if check to this one, because we now need it every time we come with this else statement. And of course, we just return the gravity value. And now if we go back up to player slope, this is what we're all here for. All we're doing is we have It's going to return a vector 3. We call it player slope. We're going to create a vector 3. We're going to call it calculate player movement. And we're going to give it our current player move input. Just again, so that we have something local we can alter. And then when we're done, we'll return it. So that when we go to our fix update loop, we can just see what's changing what easily. If the player is grounded, we want to check see if we're on a slope. So we need to know the angle of the ground below us. What we're going to use for that is we're going to use our ground check hit raycast, the one that we're using for our ground checking. We're going to use the same one. If we're grounded, that's going to get a hit. We want the normal from that hit. We'll talk about this more in a little bit. And we're going to convert that from world space to local space because we need to know the angle of the hit relative to our player. Next, we're creating a float value. We're calling that one ground slope angle. And we're going to take vector 3. We're going to make an angle from it. So we're getting two vector 3s, two directions basically. And we want to know the angle between our local ground check hit normal, which is what we just created up here, and our rigid body transform up. So basically the up of our player, or the up relative to our player, and the angle of the ground. And we want to know the angle, the amount of degrees between those two vectors. With that, we can check to see if our ground slope angle is not 0.0f, right? So if it's anything but 0, then we're on a slope. So if we are on a slope, these are the two magic little lines that are going to take our 3D input and make it take into account our 3D terrain. In the first line, we're taking a quaternion, we're calling it slope angle rotation. We're using Unity's built-in quaternion function called FromToRotation. And what FromToRotation will do is it'll take two directions, one say to the left and one to the right, and it'll tell me in a quaternion format what kind of rotation I need to do to go from the left to the right. So for our use case, we want to know the amount of rotation necessary between our player up and the current ground angle that we're standing on. And that's so that we can take our calculated player movement, we take our slope angle rotation, which we just calculated, and we times it by our calculated player movement. And that is exactly what's going to modify our 2D vector, basically, into a 3D vector. So something to keep in mind from this point on is that our calculated player movement was only an X and a Z up to this point, but now we're going to have a Y factor if we're on a slope. And that's because we are multiplying our quaternion slope angle rotation times our actual input, which was originally again an X and a Z, but now we're going to be adding a Y into that as well because we're going to be moving up or down. If that still isn't quite making sense, don't worry too much about it just yet. We're going to be talking a lot more about this. But let's keep going for now. Next, we're doing, if we're in the Unity editor, so if we're just doing a playtest basically, we're going to draw a ray. That's going to be basically pointing in the direction that we're telling our player to go. But it's going to show our modified direction, just to make sure that it's equivalent to what our slope angle is, so forth and so on. Okay? And that color is going to be red, and it's only going to stay for half a second. And then finally, we're going to return our calculated player movement. And we're back to this amazing drawing that I made for you. And we're going to go a little more in depth in what exactly is happening here. So I'm going to break it down for you a little bit more. So in the first line, you'll see that we're creating a vector 3 called local ground check hit normal. And we're using the built-in Unity function called InverseTransformDirection. And we're getting the inverse transform direction of our ground check hit normal. Okay, for now, let's focus on the ground check hit normal. And we'll come back later and we'll look at what exactly the inverse transform direction function does. So the ground check hit normal returns a normalized vector 3 that is a direction. And not just any direction, it's the normal of the surface that we're on. And what the normal is basically the direction straight up from the surface with two 90-degree angles on each side of it. So if we are on this slope right here, the normal is going to be that direction right there. This angle here is going to be 90 degrees, and this angle here is going to be 90 degrees. This is the normal directional value. Now, I don't want to spend a lot of time in this video teaching the fundamentals of geometry, so if you have any questions about the more basic stuff that I'm going to be skipping over here, or if something's just not clear to you, please feel free to go ahead and ask those questions in the comments and I'll get back to you. Let's go over real quickly how this directional value gets stored in a vector 3. So a vector 3, of course, has three different vectors. It has an X, a Y, and a Z. Let's just say that our X is forwards of our character. So it's effectively going to be the left and right on this screen. Our Y, of course, is up and down. So we have our Y, this is our X, and then our Z is going to be forwards and backwards, right? Just to keep things simple here, we're going to assume that our Z is always a 0 value, and we're just going to deal with a 2D vector basically here with the x and the y. So if we wanted to store an up direction in a vector 3, all that would look like is that would be a 0, a 1, and a 0. Now I mentioned earlier that the normal of our ground check hit is normalized by default, and what that means is that our value is a maximum of a 1 or a minimum of a -1. So in this case we're going up, our y value is going to be a 1. If we were going down, our y value would be a -1. If we were going to the left, our x would be a -1. If we were going to our right, our x would be a 1. And for the sake of mentioning it, with our z value here, which again is forwards and backwards, but we're not really dealing with that here since it's kind of a 2D drawing. But if we were going forwards, you were pushing on your monitor basically, then that value would be a 1. And if you're pulling it towards you, that value would be a -1. And that's how a normalized direction gets stored within a vector 3. Hopefully that makes a little bit of sense. Again, if you have any questions, let me know, because I definitely just brushed over that really quickly. Okay, now that we know the normal of our ground check hit is basically the direction that is perpendicular to the surface that we hit, and that is stored as a vector 3 with normalized values, let's move on to talking about the ground check hit itself real quick. If you watched the previous video where we implement our ground check, you'll know that our ground check is simply a sphere cast, and a sphere cast is similar to a ray cast in its use, except it's obviously a lot larger since it's an entire sphere. And if you haven't watched the previous video where we implement our ground check, I strongly suggest you go back and watch it so that you know what exactly is happening here. But anyway, the sphere cast is spawned at the center of our player, so right there. And like I said before, our sphere cast is a sphere, so here it is represented as a 2D circle. And we have it traveling downwards a set distance, so that the very edge of our circle here goes just below our player. If the sphere cast travels this distance and does not contact a collider before it reaches the end of its travel distance, then the player's ground global variable gets set to false since the player is not grounded, and the ground check hit global variable will have no collision return data for, so it will have mostly no values. Otherwise, if the sphere cast contacts a collider before the end of its travel distance, which again, from here to slightly below the player, that's the maximum travel distance it can go, if it contacts a collider before it reaches the end of that travel distance, then the player's grounded global variable is set to true for that fixed update loop. The player is considered grounded, and we store all of the collision data in our ground check hit global variable. The code snippet we're looking at below is actually contained within an if player is grounded statement, so that we're not executing code needlessly every fixed update loop, and so that we're not trying to access our ground check hit.normal when the normal is just a null value since there was no collision to collect a normal from. That basically sums up how we're getting the normal from our ground check. Hopefully it makes sense because I know I brushed over that pretty quickly as well. Unfortunately, this video is already getting pretty long and there's still a lot to cover that's more important than these tidbits. Next, let's review what exactly Unity's built-in InverseTransformDirection function does. That's a mouthful. The InverseTransformDirection function converts a vector 3 direction from world space to local space. To give an example of the difference between the two, I've drawn this amazing top-down view of our player right here. So over on the right side, this is our player in the middle. That's our player. And again, we're looking down from the top, so it's like a God view. We're looking at the top of our player's head. Our player is facing this way. Up in this corner are the world coordinates. You can think of this sort of like this is north, this is south, this is east, and this is west, right? So you have our X and Z coordinates. But when our player is moving or facing this direction, his local coordinates are going to be a little bit different. This way is going to be his Z coordinates, and this way is going to be his local X coordinate. So you can kind of see what happened here. If the player was originally headed this way, right, he actually turned 90 degrees to the left. So his local coordinates are going to stay the same, regardless of which way he is orientated, but the world space is always a constant. That's why it's applied to the entire world. So again, to summarize, local space is relative to the game object the script is attached to, in this case, our player. Its local coordinates will always rotate with the player, and the player's forward will always be the positive Z coordinate. Whereas world space is pretty self-explanatory in that it is constant and does not change. This may not seem very important right now, but this is critical to understand, and I'm sure we'll touch base on this again yet in this video. But right now, we finally get to move on to calculating the angle of the ground that we are on. So here we're creating a float, and we're calling it ground slope angle. We're using Unity's built-in vector3 function called angle to find out the angle between our ground check hit normal and our rigidbody transform up, which sounds complicated, but we now know that our ground check hit normal is this direction, right? And our rigidbody transform up is simply just our player up. So all we're doing here is we're finding out the angle between these two. And through the power of some simple geometry, we can know that the angle between these two is going to be the same as the angle of the ground that we're standing on. And that's because of a few different things, which I'll touch on just very quickly here. First, we're using our players up here because we need this angle to be consistent regardless of our player's direction of travel. In other words, we do not want to be using something like our player's forward vector. Like for example, this would be our player's forward vector. We do not want to be using something like our player's forward vector since we will not always just be moving forwards. We can be moving backwards or even strafing or sidestepping left or right? So we can't be using something that's just limited to moving our player forward. We need to be using something universal like our players up. So by using the universal player up vector, we're getting a direction that we can use universally regardless of our player's direction of travel. Second, our players up is perpendicular to perfectly level ground. And what that means is if we have perfectly level ground, our players up is 90 degrees of that, right? And our ground check hit normal here is perpendicular to our slope, or our ground anyway. Hence why when we get the angle between the two of these, we get the angle of the ground our player is standing on. So I hope you see the relation there. These are basically fixed points to the ground. This is a fixed point to always be in level ground. So this angle is always going to be the same as this angle. And just in case to drill that just a little bit further, we'll keep scribbling on this terrible drawing. So again, our normal here is affixed to our slope. If our slope were to start leveling out and we got a less serious slope, our normal would then be about there, right? It would just start rotating along with it. It would move as necessary along with our slope. Because again, this is perpendicular, it's fixed, it's always going to be 90 degrees. So if it's always going to be 90 degrees, then it's going to, again, it's rigid, it's fixed, it's going to be moving with that ground, which is going to increase and decrease the angle between our players up and the normal. So yeah, it's just a effective universal way of getting the angle of the ground that we're standing on regardless of our direction of travel. Okay, hopefully you're still with me so far. Next line, if we're not on a ground slope angle that equals 0 degrees, then we are on some sort of slope, and we're going to execute this next code where we're creating a quaternion called slope angle rotation. We're using Unity's built-in quaternion function called FromToRotation, and we're finding out the rotation from our rigidbody transform up, or our players up, to our local ground check hit normal. So this should be pretty easy to explain now, since we've come this far. And the name itself, the quaternion FromToRotation, is pretty self-explanatory. It's literally a FromToRotation. So let's just draw this out real quick. So our FromToRotation, where are we rotating from? We're rotating from our player up here. And where are we going to rotate to? We're going to rotate to our local ground check hit normal. So we're going to rotate to here, and we want to find out what it'll take to convert a vector3 that is going this way to rotate to a vector3 that is going this way. So if you remember, our 2D movement input is telling our player to go forwards, off into air here, but we really want to take into account this slope so that we don't go skipping down it. We want to move smoothly down it and up it. All we need to do is take this rotation we just calculated from the normal of level ground to the normal of the ground that we're on and apply that to our 2D movement input vector to get our 2D movement input vector to take into account the 3D terrain that we're navigating. So we've gotten all the angles that we need, we've gotten everything together we need, we've calculated the rotation necessary. All we gotta do is add it all together, and we're gonna have our modified movement vector, which leads us right into our next line of code here, where we take our calculated player movement, and we're saying it equals our slope angle rotation, which is our quaternion based rotation that we generated from angle to angle, right? And we're just simply multiplying it by our calculated player movement. And that's going to modify our player movement into our new player movement, which takes into consideration the angle of the ground that we're on, and we're done. That's it. Our movement, instead of going forwards like this, is now going to go down the slope. And traversing slopes properly is as simple as that. although it took quite a bit of explanation to get here, and that's with me brushing over a lot of things and skipping some things completely. So if you have any questions, please feel free to ask them in the comments. I'd also greatly appreciate if you left a comment letting me know whether you like this style of video or not. In this video, I'm trying to go more in depth on some things and explaining important concepts multiple different ways. I'm not sure if that helps or not, or if you find it too repetitive. At any rate, let me know your thoughts. Also, if you found this video to be helpful, then I'd appreciate it. If you like this video, consider clicking the subscribe button. Doing so will greatly help encourage me to keep creating better and more helpful content for you. So go ahead and help me help you by doing that now while I get us ready to do a playtest of our code so far. Okay, hopefully I gave you plenty of time to do that. I really appreciate you commenting, liking, and or subscribing. It really does help a lot. And without further ado, let's see how our character handles slopes now. We're going to go ahead and run up it. And you can see we go up it without any speed change. That's great. And if we go down it, see if I can do it without going off the edge. You can see we don't skip at all. It's a nice smooth motion. But also notice since we're going down, we're not actually accelerating or going any faster than when we go up, which is fine. We can always modify that however we want later, which we're still going to do in this video yet. So we still have quite a bit to do. We don't have any slope limits either. We can go up any steep slope as long as our ground check is still being returned as true. As long as our player still thinks it's grounded, it's going to work. So yeah, if maybe this is all you want, you can stop here if that's all you need for your game or your project that you're working on. Let's unmaximize the play window so we can look at things a little bit closer. So over in the inspector panel, if you look at our speed, you can see that our maximum speed on the ground is about 17.25. So on a flat surface, our max speed is 17.25. If we go up this 55-degree slant, you'll see our max speed still tops out at 17.25. If we go down it, same thing, 17.25. So we are definitely going the same speed. I'm going to stop the game now. I'm going to add a visor for our player. That'll indicate the front of our player so we know which way our player is facing at all times easily just by looking at it. I should have done this from the start, but it's just one of those things I skipped over, but we're going to take care of it right now. Okay, now that's done, if we go back to our character controller real quick, our humanoid land controller script, I just want to remind you that we have this line here executing. And again, this is just going to draw a red line in the direction of our calculated player movement, and that's just for debug purposes. I'll show you exactly what that does here. Back to Unity now, and we'll play the game. You're going to want to look at our scene window more than our actual game window, because our scene window is what's going to show our debug lines that we're drawing. As we move over to slope, you'll see the red debug lines being drawn on the scene window, or in the scene window rather. And whatever direction I am applying force, whichever direction I'm telling my character to go, you'll see the red lines are doing that. It's just a visual representation of where the force is being applied on our character. I'm using a gamepad right now, which makes things a lot simpler and gives a better idea. If I just go forwards, and I change the actual look of our player, you can see how that affects it. If I go up a slope, see the lines go up, as well as down. I can go up it sideways, doesn't matter. Go up at an angle. Everything's working perfectly. So yeah, that's really cool that we accomplished this. I hope you're excited about this. This is pretty cool. I was really happy when I figured this out, but we're still not done. Next, we're going to make our player go slower when he goes up a slope, and faster when he goes down a slope, as well as set a maximum angle of the slope that our player can climb. So we'll stop the game. We'll go to our humanoid land controller in our project panel and open it up in our editor again. And in our player slope function, I'm going to go ahead and add the two lines that we need to do what I just talked about. Okay, and let's go over this code real quick. We're creating a float called relative slope angle. We're using Unity's built-in vector3 function called angle, and we want the angle between our calculated player movement and our player up, and we're subtracting basically 90 degrees from that angle. In the next line, we're taking our calculated player movement and we're adding to it our calculated player movement times our relative slope angle divided by our max slope angle. Which, if you remember earlier in the video, we set up our max slope angle variable and we set it to 47.5 for now. You can set whatever you like. You can also call these variables whatever you like. Obviously, you can do whatever you want with this code, but here's the rough formula. Anyway, I feel like I should break this down for you more and go back to our drawing board, but you've probably already had enough of my terrible drawings already. What's that? You haven't? You want more of my terrible drawings? Really? Well, I'm surprised. I am surprised, but I will not disappoint. Now, a quick disclaimer, there may be a better way of doing this. I don't know, this is the first way I thought of doing it. It's pretty simple. But if you do have a better way you want to share it, that'd be awesome. I'd really appreciate that. That'd be great. So let me know in the comments below if you think something better, but here's what I've got. So before we were using our player up, which is this guy right here, and we're using our ground normal, which is this guy here. But we need to know if we're going up the slope or down the slope. So since we now have our calculated player movement, taking into consideration the slope, we can just use our calculated player movement, which is either going down the slope or up the slope, right? And we can compare these to our player up. So for example, let's just say that we know we're on a 45-degree slope, which means that if we were going backwards up this slope right now, this direction up here would be 45 degrees. Okay? And this direction here, relative to our player up, is going to be 135 degrees. So then what we can easily do is simply just subtract 90 degrees from either of these numbers, and we're going to get negative 45 and positive 45. And that's it. That's all that line's doing. It's just getting a positive or negative number of degrees, basically, depending upon whether we're going downhill or uphill. And the next line isn't much more complicated. It's actually a little simpler. We're just taking our calculated player movement, and to that we're adding our calculated player movement multiplied by a percentage, which is our relative slope angle divided by our max slope angle. So for the sake of simplicity, let's say our max slope angle is 90 degrees. And our relative slope angle is 45 degrees. We're going to divide 45 by 90. We're going to get 0.5, which is equivalent to 50%. So we're basically just taking this 0.5, we're multiplying our calculated player movement by it, and in the end we're going to get half of our calculated player movement back. And then we're going to add that to our calculated player movement, which means if we're going 45 degrees downhill, we're going to go 50% faster, or add 50% more force anyway. Likewise, with going up a hill, this is a negative value, so this is going to come back as a negative 0.5 or negative 50%, and when you add a negative number, we're going to take away 50% of our player movement when we're going uphill. And it's really as simple as that. Of course, this calculation is completely linear in its ramping, but you can always change that to whatever you like if you prefer it to be non-linear, which I imagine you would in most games. I also realized I didn't go over this section of code as in-depth as I did the previous section of code, but this section of code is a lot simpler and it's not that important. Some people might not even want to use it, but as always, like I've said a million times already in this video, if you have any questions, ask them in the comments. I'll be happy to answer if I can. And with that, we can go ahead and go do a playtest. And if we head over to a slope now, we go a lot slower up the slope. We still move just as fast going laterally. If we go down the slope, we go a lot faster. So this will be a good example here. Go up it slowly, go down it quickly, up it slowly, down it quickly. And if we try going up 45, we'll go up it very slowly. We'll go down it very fast. And the 50 we can't go up because that's just barely past our slope limit. You can see we slowly go back down it. Same with 55, that's further past it, so we'll go back down it faster. And everything is working. Again, we can still go up it sideways, or even backwards, very, very slowly. And we can go down it any which way as well. So, direction does not matter. Okay, now with all that said, there are issues with what we have so far. For example, if we go up this and we let go of our controls, we'll just stay here. That's a problem. Another problem is if we go up it and we keep trying to go up it, we will bounce. That's another problem. And the final problem is if we go up this at an angle, we can actually still slowly go up it, which makes sense, kind of. But we ideally don't want this to happen. Also, if you go up it at an angle, you'll actually go up it faster than what you otherwise normally would. For example, this 45 will go up at an angle. See how we go faster? Yeah, that's no good. I mean, some games might allow for that, some games that might be okay. In this case, I'm going to show you how to fix that, and all that's going to be in the next video. That's it for this video. I hope you found it helpful. Let me know in the comments below if you did. The more I hear from you, the more motivated I am to get these videos put together and uploaded. So if you find these helpful, be sure to like the video and don't forget to subscribe and tick the bell to be notified of new videos when I post them. As always, thanks for watching, and I appreciate you. If you're feeling generous, leave a comment down below. I want to read what you're thinking. Let me know if you have any questions or recommendations. I'd also appreciate it very much if you liked the video. And if you're feeling extra generous, it'd blow my mind if you subscribe to the channel. Being new to this and putting these videos together takes a lot of time and effort. Thank you for any and all participation and support. I look forward to continuing this in the next one. See ya.